exam, and also we're going to discuss some problems as a review, and you're going to have the chance to ask questions. Okay, so Wednesday, come prepared with questions, because on Monday we're going to have our first exam. Okay, so the last material that is going to be included in that exam is the material that we're going to cover today, and this is the lecture that we start on Wednesday that discuss random variables and probability distributions. So we still know our second objective for this course, and here's the map or the outline of the topics that we have covered so far. These are the concepts that you should study for your exam as well. So we started with the statistics, and then we discussed the concept of the sample, an event, how to count sample points, and also how to compute the probability of an event. So today we're going to add to that, we're going to discuss random variables and how are they related to sample and also probability distributions. So the outline for this lecture, again, we have 4 bullets. Understand the concept of the random variable, discuss what is a discrete probability distribution, what is a continuous probability distribution, and what is the difference between those two. That last bullet is not going to be part of the exam. So that's a material that we're going to cover after the exam, which is joint probability distributions. So the learning objective so far, again, want to make sure that you understand those concepts for the exam. We're going to talk about those, specifically those concepts in blue today. So the concept of random variable, as we stated on Wednesday, statistics is concerned with making inference about population and population characteristics. For example, the testing of a number of electronic components can be classified into defectives and non-defectives, and that type of classification, if you're collecting data from your manufacturing process, can be classified as a statistical experiment. So to give you, again, to remind you of what we're trying to do, we're trying to collect information from population, because we cannot analyze all the data from the population. We're trying to get some data from the population. That's what we call a sample. But we want to make sure that we collect a sample that is good enough, that is going to allow us to provide some inductive reasoning about the population using statistics. Okay, so that's the general concept or the general idea of what we're trying to do in this course. So we're still discussing ways to compute probabilities so we can get to that part in which we can connect a good sample from our population. Okay, so it is often important to allocate a numerical description to the outcome. So we know how to collect or how to describe a sample, how to describe an event, but usually what you need is a number or provide a number or classification to that specific outcome of your sample space. So for instance, the sample space giving a detailed description of each possible outcome when 3 electronic components are tested. You can provide a number depending on the number of defectives that you find in each outcome. So for instance, here you have 0, no defective. And I'm looking at this row under the sample space. So here you have 1 defective, 2 defective, 1 defective, 2 defectives, and so on. You can also define another random variable by looking at the number of non-defectives, which is going to be the opposite. So you have, instead of 0, you have 3, 2, 2, 1, 1, 1, and 0. Okay, so what we're trying to do here is to define a number for each outcome. That definition of that number or that function is what is a random variable. This is a random variable. Okay? So what is concerned with the number of defectives that occur? Each point in the sample space will be assigned a number or numerical value that will go from 0 to 3. And the reason for that is that you cannot have more than 3 defectives because that's the limitation of your sample point or your outcome. If you were to have 4 outcomes or 4 or electronic components for each outcome, then you know that you can have from 0 to 4. But in this case, each outcome contains only 3 electronic components. Okay? So the values will go from 0 to 3, and these values are random variables assumed by what we call a random variable x. Okay, so any questions until this point? You're just looking at the sample space, and we are assigning a function that will give us a number for each outcome. And that's what we define as a random variable. Okay, so the definition, a random variable is a function that associates a real number with each element in the sample space. And that's what we did with the example. We shall use a capital letter to say, for example, x, to denote a random variable, and its corresponding small letter is, in this case, one of its values. So if you want to show or describe the value of the random variable, then you use the small letter of that random variable. The capital letter would denote the actual random variable with all the values. So the other example that we discussed on Wednesday was this very easy problem in which you have 2 balls that are drawn in successions without replacement from an urn containing only 4 red balls and 3 black balls. So the possible outcomes and the values of the random variable y. So instead of using x, now I'm using y to define the random variable, where y is the number of red balls. So if you draw 2 from this urn, these are the possible outcomes that you can have in your experiment. So you can have 2 reds, 1 red and 1 black and 1 red, or 2 black. And based on the description of the random variable, which is the number of red balls, you can provide a number for your sample, for each outcome of your sample. Okay? This is another example. So here we have a stockroom clerk returns 3 safety helmets at random to 3 steel mill employees who had previously checked them. The name or the last name are from these employees are Smith, Jones, and Brown, in that order. Receive one of the 3 hats. So now I want you to list the sample points for the possible orders of returning the helmets and find the value m of the random variable m that represents the number of correct matches. So we are returning these helmets and want to know if we were able to match the exact same person. So if we were to define this sample space, I'm going to use the last name to call the employees. So number 1 is S, this is Smith. Number 2 is Jones. Number 3 is Brown. Okay, so my sample space, basically the order, or how do you order these 3 persons. So you can put S, J, then another combination could be this one, another one, another one, and the last one. Okay, so those are all the possible combinations for these sample space. And now I want to see the number of matches depending on the order. So the order is Smith, Jones, and Brown. So for the first combination, I have all of them. So the value of the random variable will be 3. Again, this is the order that I'm looking for, Smith, Jones, and Brown. So the second one, we only have 1 match, 1 match, 1 match, and then 0 and 0. So if you were to define that random variable, that represent the correct number of matches, then these are the possible values for that random variable. Any questions? So again, we are trying to assign a number to each possible outcome of your sample space. You define your sample space, you define the function, in this case it's the number of matches, and then depending on that function, you represent the value with a number. Now we have another example. Consider the simple condition in which components are arriving from the product line or production line, and they are stipulated to be defective or non-defective. So if you were to define a random variable for such a process, then you know that you only have two possible outcomes, defective or non-defective. So one way to represent that using a number is using binary. So if it is defective, you can use a 1, and if non-defective, you can use a 0. Okay? The random variable for which 0 and 1 are chosen to describe the two possible values is called a Bernoulli random variable. Okay? And this is important because we're going to define functions that are based on this type of random variable. So the Bernoulli random variable, when you say Bernoulli random variable, you're basically referring to a random variable that only assume values 0 and 1, or binary values. Okay? And we're going to come back to this concept later in this course. But keep in mind, a Bernoulli random variable is one random variable that assumes values of zeros or ones. So, again, statisticians use sampling plans to either accept or reject batches or lack of materials. So suppose of these sampling plans involve sampling independently 10 items from a lot of 100, in which 12 are defective. We can define a random variable. So let's say let x be a random variable defined as the number of defective in the sample of 10. Then x can assume values that go from 0 to 10. Right? Because if you choose 10 or you pick 10 from this lot, you know that are 12 defectives. That random variable can go from 0 to 10. If you only had, let's say, 7 defectives in this lot, then that random variable will go from 1 to 7. Just because the way that you're defining the random variable is based on the number of defectives. Okay? Now, suppose that sampling plan involves sampling items from a process until the defective is observed. The evaluation process of the process will depend on how many consecutive items are observed. So this is a different way to define the random variable. Now we are interested in the evaluation and how many consecutive defectives are observed. So we can define a random variable, let x be a random variable defined by the number of items observed before a defective is found. So we can define this as non-defective and defective. So X will be on this outcome if we know, or if X equals 1, right? Now, if the sample space equals ND, then we know X will equal 2. And as the number of non-defectives increase, you know that the value of your random variable will also increase. So last one, so if the sample space equals N and D, then we know X will be equal to 3, and so on. So the way you define your random variable is what's going to affect your sample in this case. Also, it will affect the values or the numerical values of the output. So as an experimenter, you need to define what's the detail that is important or what you're trying to achieve in your experiment. Such as, I don't know, such finding the number of detectives in the particular process. So once you find that question, you can define your random variable and start performing your experiment. So up to this point, we've been focusing on defining random variables. One more example. Let X be the random variable defined by the waiting time in hours between successive speeders spotted by a radar unit. So what will happen with this variable? Remember any concept to define such type of variable? This is not a Bernoulli, but the interesting thing about this random variable is that you cannot define it by an integer number, because these are waiting time. So this type of variable will be a continuous random variable. Okay, so if you were to define this, then the random variable X takes on all values X for which X is greater or equal to 0. Okay, so we're going to discuss this fact more in detail later in this lecture, but this is just to give you an idea that not all the variables are easy to define by numbers, because sometimes you have continuous numbers and then you have to use a different way to define those random values. So in this case, we just define the values based on the this greater or equal operator. Okay, so we have now two definitions. The first one, if the sample space contains a finite number of possible or unending sequence, which as many elements are there, whole numbers, that is called a discrete sample space. Okay, so now we are making that distinction. So discrete sample space, finite numbers of possibilities. Now, if we have a sample space contains an infinite number of possibilities, then equal to the number of points in 9 segment, then that type of sample space is called a continuous sample space. Okay, so continuous random variables, discrete random variables. Continuous random variable will come from a continuous sample space. Discrete random variables will come from a discrete sample space. And these are the differences. Now, go more in detail. Random variable is called discrete random variable if it is set of possible outcomes is countable. So you can count the number of outcomes. Represents count data. So the number of effectives in the sample of X number of items. Or the number of highways fatalities in 1 year. That's another example. Now, when a random variable can take on values on a continuous scale, it's called a continuous random variable, represents measured data, for example, all possible heights, weights in this classroom, temperature, distance, light periods, which are not discrete random variables. Okay, so you can count the number of outcomes, then you know that you're dealing with discrete sample space. You're using discrete random variables. But when you're trying to represent measurements, then it becomes more difficult because this measurement can take any values within a line segment, can include decimal points. So these are represented using continuous sample space, and I call continuous random variables. Okay, so now I want you to work on this problem individually. This is not for submission. This is just to see if you understand the concept of a random variable that is discrete and a random variable that is continuous. So if you don't have the problem with you, let me know if you can read it from the back. And just from each of these items, let me know if it is a random variable or a continuous random, a discrete random variable or a continuous random variable. Now I'll give you 2 minutes to complete the exercise. So discrete, you can count the number of outcomes in your sample space, but it's not possible to count the number of outcomes in your sample space, then you use a continuous random variable. Done? Start with the first one, the time until a projectile returns to Earth. Set continuous or discrete? Continuous, correct? B, The number of items a transistor in a computer memory changes state in one operation. Discrete, correct. The volume of gasoline that is lost to evaporation during the filling of a gas tank. Discrete or continuous? Continuous, correct. The outside diameter of a machine's shaft is a measurement, remember. So measurements are continuous random variables. Okay, it could be 11.64. So if it is not an integer value, then you know that it's a continuous random variable. The number of cracks exceeding 1/2 inch in a 10 miles highway. Discrete, correct. The weight of an injection mold plastic part. Continuous. The number of molecules in a sample of gas. Discrete, correct. The concentration of output from a reactor. It's continuous, correct. And the current in an electronic circuit. Continuous. Any questions? Okay, so it's important that you understand the difference between the two, because now we're going to take this step further. We're going to discuss now how to define probability distribution for each type of random variable. Okay, so we define a sample space, we describe the sample space based on discrete or continuous. So based on these two concepts, we can define some functions or probability functions for these type of random variables. So we're going to start with the discrete case. So discrete probability distributions. So a discrete random variable assumes each of its values with a certain probability. Represent all the probabilities of a random variable x by a formula. Okay, so such a formula will necessarily be a function of the numerical x values, and that will just denote that function using one of these terms, and so forth. So the most common term that we use to denote the function is f of x. So this is a function of x. Okay. So the set of ordered parts x, f of x, is called a probability function. You provide a value, and you want to know what is the function value based on this value that is provided. So the probability function, a probability mass function, or a probability distribution. So the only term from this list that is used for discrete variable and not for continuous is the probability mass function. So if I describe a probability mass function, then you know that I'm talking about discrete random variables. But a probability function can be used also for a continuous random variable, and probability distribution concept can also be used for a continuous random variable. Again, the only one that is not used for continuous random variables is the probability mass function. So this is the most formal definition of a probability function or probability mass function of the discrete random variable x. If you satisfy these three conditions, then you know that you have a probability mass function or a probability distribution for a discrete random variable. So the first condition is that function, when evaluated in x, is always greater or equal than 0. Okay? If that function, if you evaluate that function for one value of x and it's not greater or equal than 0, then you know that that is not a probability mass function or a probability distribution. Second condition, the sum of all the probabilities values always equals 1, and the probability of that random variable being equal to a value x is always equal to the value of that x evaluated in the function. Okay, so this is again the conditions that are necessary to define a probability distribution for the discrete random variable. Let's look at this problem. And here we're going to use several concepts that we already learned from this course. And so this is a good example to see if you can put together some of the pieces that you already learned. So we have a shipment of 20 similar laptops computers to a retail outlet. Contains 3 that are defective. From this lot, 3 of the items are defective. If a school makes a random purchase of 2 of these computers, find the probability distribution for the number of defectives. So now I'm asking about the probability distribution. I'm not asking about the random variable, but we still need to define a random variable to get to the probability distribution. Okay, so let me define that random variable. So x be a random variable whose values x are the possible number of defective computers purchased by the school. So what are the values that this random variable can assume? 0, 1, and 2. Because there are 3 defectives from the lot, and you are buying 2. Okay, so from the lot, you can select 1 that is defective, you can select 2 that are defective, or none of them being defective. Okay, so those are the possible values. Let me put that here. So x can only assume values 0, 1, and 2. Okay, so we define the random variable, but now we need to find the probability distribution, and this is something that you don't know how to do, so I'm going to try to walk you through the process. Something that we know is that to compute the probability of an event or an outcome to happen, we need to know all the possible or the number of combinations or the number of outcomes from the sample space. So that's the first thing that you need to know. What are all the possible outcomes of the sample space? Because when you find the number of outcomes from the event that you're defining using your random variable, you want to divide that number of outcomes by the total number of outcomes. And that will give you the probability of that specific outcome. Okay, so by theorem 2.6, so by theorem 2.6 says that the number of combinations of n distinct objects taken R at the time is equal to nr, where this equals n factorial divided by r factorial times n minus r factorial. Okay, so we know that from our previous lecture. So now I want to know what is the probability function for this random variable, and I know that this random variable can only assume 0, 1, and 2 values. So I want to know what is the probability of having x equals 0. So that probability is defined by f of 0, and this is going to be equal to the probability of x being equal to 0. Okay, so now I need to define the number of outcomes for such an event. So for this event, we're trying to find the number of defectives, right? So the number of defectives equals 0 for this case, probability of x equals 0. And using the number of combinations, I can use the multiplication rule to find the number of outcomes for this event. Okay, so I'm showing you that right now. So that event is going to happen when you select 3. From the 3 that are defective, you select 0. And from the ones that are non-defectives, you select 2. That makes sense? You're trying to define the event in which you select none of them are defective. And that will only happen when from the group that are defective, you select 0. And from the group that are non-defective, you select 2. Okay, so we are using the multiplication rule. We are trying to find out the number of outcomes that satisfy that condition. And that is found using the event in which you select none of them that are defective, and the event in which you select 2 from the ones that are non-defective. So that will give you the number of outcomes from the sample space that satisfy that condition. And now in order to find the probability, you need to find the total number of outcomes for selecting 2 out of 20. So that is 20 out of 2. That expression defines, and the result from that expression gives you the probability of x being equal to 0. Now, in order to solve this expression, then you need to compute these for each case, multiply these 2 and divide by using these outcomes. That total is 68 over 95. And then I'm going to let you solve that using your calculator. Okay? Now, we need to perform the same operation for the probability of x being equal to 1. So, probability of x being equal to 1 is the probability of x equals 1. So we go through the same process. Okay? So now we want to define the same function, but for the case in which x equals 1. So that will happen when you select from the 3 that are defective, you select 1, and from the ones that are not defective, you select 1. The denominator will be the same. And this equals 51 over 90. And we can do the same thing for f of 2. This will happen when the probability of x equals 2. And this is equal to 3. You select 2 defectives from the group of 3. And you select none from the group of 17. 20 out of 2. And this is 3 over 190. So again, this is a discrete random variable. We are defining the discrete probability distribution. So we found the probability for each one of the values of that random variable. This, and this. So now we can create a table that will basically put together all the probabilities So the probability distribution of x. So for x, we have a f of x. So for x equals 0, f of x is 68 over 95. For x equals 1, the probability is 51 over 90. And for x equals 2, the probability is 3 over 190. And that's your probability distribution for that random variable. Anyone can tell me what would happen if you have this number, and this number? It should be equal to 1. And it will be equal to 1. Okay? Because the probabilities always add to 1. If it doesn't add to 1, then there's something wrong. This operation that we described for this random variable, this operator, this function, is a probability distribution that is defined already. It's called the hypergeometric function, and we're going to discuss it in detail later in this class. Okay? So there's a definition, there's a lot of study done in that particular function or probability distribution, but I just wanted to give you an idea of how you can come up with it without having the actual definition. Okay, so that's how you define the hypergeometric. Any questions? Okay, so important things from this problem: you define your random variable, you find the probability for each outcome of your random variable, and then you define your distribution. You define your distribution. When you add those numbers, you need to make sure that those numbers add to 1. We have another example. If a car agency sells 50% of its inventory of a certain foreign car equipped with side airbags, find a formula for the probability distribution of the number of cars with side airbags among the next 4 cars sold by the agency. So how would you define such random variable? So you're looking at the next 4 cars and you want to know how many of them are equipped with airbags. So you can use an outcome. Let's say A is airbag and is no airbag. And you know that the possible outcomes for this random variable are going from 0 to 4. So let me call this x values 1, 2, 3, 4. So for this problem, it's very easy to define the number of outcomes. So you have 2 options and you have 4 elements. So 2 to the 4, this is 16 points or outcomes. And we can define them. So your sample space are n, 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 a, and so on till you get to a, and a. Meaning that for the first one, no airbags for all the next 4 cars, or you can have also no airbag for the first 3 and the 4th one, and so on. The last one outcome tells you that you have all of them with airbags. So you know that you have 16 points in your sample. That should give us an idea of how to compute the probability. The other thing that you need to see from the problem is that it is telling you that each item %, of each one of the cars is self-equipped with airbags. So you know that this item here has a probability of 1/2, probability of 1/2 of has an airbag, and an airbag. Okay, so you know that each outcome will have the same probability of being selected because each outcome is random. All of them will have the probability of 1/2 times 1/2 times 1/2, and that will be 116. So 116, which is the same as saying you're going to divide one outcome out of the total number of outcomes, which is 116. Okay, that being said, now we can define a function for the probability. So this is the probability of x being equal to x. So we know that each outcome will have the probability, or you're going to divide by 16 because each outcome will have a chance of being selected by. So this will be the expression divided by 16. So if you were to define the expression for x equals 1, so the number of combinations for selecting one out of the 4 is defined by choosing one out of the 4. So one of them is going to be defective. If you do the same for, this is for x equals 1, x equals 2 will be 4 out of 2 divided by 16. So we can define a general expression that says that f of x will be equal to the probability of x equals x, and this is going to be equal to 4x divided by 16, where x will be equal to 0, 1, 2, 3, and 4. And if you solve those numbers, then we can also define the probability function. So x and f of x, 0, 1, 2, 3, 4. This is going to be equal to 116, 4, 16, 6, 16, 4, 16, and 116. And if you add those probabilities, that will be equal to 1. So this is the probability distribution of x. So if I ask you for the probability distribution of a discrete random variable, this is what I'm looking for. Okay? So the probability of having 0 cars with airbags equals 160. The probability of having 2 cars with airbags equals 6/16, and so on. So that's the second example. I think I don't have any other examples, but you can go back by yourself, review these examples, and try to understand them. If you have questions, let me know, and we can go back and discuss them. because now I'm going to discuss a different concept. This is the concept of cumulative frequency distribution. So I think we covered on the first lecture, we discussed the difference between a histogram that is defined only for the values and a histogram that is defined for the cumulative values. So when you look at the cumulative frequency distribution, it's obtained by computing total frequency of all values less than the upper class limit of a particular interval. So instead of looking at equals 5, you're looking at all the values that are less than 5. Instead of looking at equal to 21, we're looking at all the values that are less than 21. So the numbers that are contained in this range are also contained in this range. Okay? Because we are accumulating those numbers based on that top value. So there are many problems where we wish to compute the probability that the observed value of a random variable will be less than or equal to some real number. So instead of looking at equal to 17, we want to know the probability of all the numbers that are less than or equal to 17. Okay? So writing the cumulative probability distribution. So we already defined a probability distribution as f of x. So this is probability distribution, right? When we talk about the cumulative distribution, we refer to that with capital F. So this is cumulative. Okay? So it's important for you to understand the difference. So one is function, the other one is the cumulative. You're looking at those values that are less than or equal to this particular number. So for every real number x, we define f of x to be the cumulative distribution of the random value. So the cumulative distribution f of x of the discrete random variable x with probability function f of x is equal to the values of those random variables that are less than or equal to this number. For a discrete probability distribution, what we do is we add or we sum the values for all the outcomes that are less than or equal to that number. So for instance, if we know that f of 1 equals 0.2, f of 2 equals 0.25, and f of 3 equals 0.10, if I ask you for the probability of x being equal to 2, you will tell me it's 0.25, right? Because that's equal to 2. Now, if I ask you for the probability of x being less than or equal to 3, what would you do? You need to sum. You need to sum because f of 1 is included, f of 2 is included, and f of 3 is included. So the probability of x being less than or equal to 3 will be 0.2 plus 0.25 plus 0.10. And that is equal to 0.55. So this case is asking for the cumulative. This case is just the probability for that number. So in this case, this is 0.3. Okay? So it's important that you know that we're dealing with discrete random variables, and when we look at the cumulative, we sum. Concept, very simple concept. What will happen is when we discuss the continuous probability distributions, instead of summing, we're going to integrate. Okay? So I want to see you integrating for a discrete random variable. Okay? So you need to understand when it's a random variable that is discrete. By asking for the cumulative, just need to add the value. If it is continuous, then you need to integrate the function. Okay, so keep that in mind. So for a cumulative distribution, discrete random variable, cumulative is defined by the summation of all the values that are less than or equal to that x. So this is another example, stack room. It's the same example that we used early today. So let me put the sample space here really quick. So this is 3, 1, 1, 1, 0, and 0. So this is the expression that I'm using. Find the cumulative distribution when x is less than or equal to 2. So that statement, what I just said, is what that means. Because this is capital F, so you're referring to the cumulative. So that means that you need to find the probability that the number of correct matches is less than or equal to 2. Okay, so any ideas how to get that probability? You know that you need to find f of 0 plus f of 1. What is f of 0? So you have 6 outcomes in your sample space, right? From these 6 outcomes, only 2 are equal to 0. So the probability of being 0 is defined by 2 over 6. Does that make sense? So if you need the probability of 1, you have 3 outcomes that will be equal to 1, which means that the probability is equal to 3 over 6. So when you sum those two, the cumulative distribution is 5 over 6. Looks simple, but requires some understanding of the concept and also some little experience. So you need to practice in order to get these and understand it. So you look at the probability of having an outcome equal to 0. You have 6 outcomes, 2 of them are 0, then the probability is 2 over 6. Same thing for 1. 3 outcomes equal to 1 out of 6, so the probability is 3 over 6. So the cumulative probability is the sum of the two. Now, we can also define that cumulative distribution using this range. So we know the probability is going to be equal to 0 only if the number of outcomes is less than 0, which based on our experiment, that never happened. Okay, so that would have a probability of 0. There's no value that is less than 0. Now, we also have, based on these numbers, we know that we can go from 0, so equal to 0, up to 1, and that probability is equal to 2 over 6, because it includes the values in which 0 is observed. We also have another range. It goes from 1, less than or equal to n, less than 3. And for that one, this is 3 over 6. Remember, we're defining the cumulative distribution. So this is 3 over 6 plus 2 over 6. So this is 5, 6. And the last one is when 3 is included. So all the values that are greater or equal to 3, that will be equal to 1, which is 2 over 6 plus 3 over 6 plus 1 over 6. That's 1. Yes, sir. This one? Yes, you're right. Thank you. Because we are looking at the cumulative. Let me double check this. Yeah, but then last one you need to be predefined again. Because you will have to include all the last variable. Here we're looking at the outcomes. So the outcomes are defined by this column. The first one is when the outcomes are less than 0, so that never happen. The second one is when the outcomes go from 0 to 1, and 1 is not included, so that only happens here, 2 out of 6. That's correct. Then the third one, we use less than or equal to 0, greater or equal to n, less than or equal to n, to less than 3. Then it will include all these numbers, 5 over 6. So these n should be greater or equal to 0. We'll include all of them. We'll go back to this. But for now, make sure that you understand how to get the cumulative and how to get the probabilities for those outcomes that are less than or equal to a specific number. Okay, we'll come back to how to define the cumulative. And the next example is actually the same type of problem. We're referring back to the old examples. Here we find the cumulative distribution function of the random variable x using f of x and verify that f of 2 is equal to 3/8. So again, we need to go back to our probability function. So f of x will be equal to 116 times 4x. And we define that from our previous example. And now we need to find the cumulative function for each outcome. So remember, from this problem we have 4 cars, and the possible values could be 0, 1, 2, and 3, and 4. So we need to find f of 0, which we already did. That's the value of f evaluated in 0, which is 1 over 16. Then we have f of 1, get f of 0 plus f of 1, that's 5, 16, f of 2, f of 0, and so on up to f of 2. That will be equal to 11, 16. Then we have f of 3, which is equal to f of 0 up to f of 3, 15 over 16, and then f of 4, and this is 1. Okay, so we are finding the cumulative values for each outcome. We know that the outcomes in this specific example will go from 0 to 4. So the values will be the evaluation of the function. For f of 0 is the evaluation of the function, 0. But when you go to 1, since we are looking at the cumulative distribution, we need to look at the values that are less than or equal to 1. That's why we use 0 and 1. And we add the values for those two. The process is repeated until you get to 4. When you add the last outcome, you need to make sure the summation of the probabilities equals 1, which is the case in this problem. Now, we need to define the cumulative probability distribution. So that's why I came back here. And I think now I found out what is the misunderstanding. Okay, so we'll define f of x. Again, we are trying to find the cumulative distribution. So when you define this range, let me go back to the previous problem. So this should be 1. Let me go write this. And this should be 3, as I stated early. And the reason why is you're looking at the cumulative. You left 0 here, then you're saying that for n equals 0, the cumulative distribution will be 1, which is not the case. For 0, the cumulative is 2 over 6. Okay? So you're looking at n. What is the cumulative value or the cumulative probability for that n? So if n equals 1, you know that the cumulative is 5 over 6. Which is not the case when n equals 3, because you know that the cumulative for n equals 3 will be 1. Okay? So the limits are based on the actual value of n. Okay? So we're going to do the same thing for the next problem, and I think that's the last thing we need to do for today. I think we can discuss one more thing. Okay. So for this case, again, we are looking at these numbers. So the cumulative will be equal to 0 only for x less than 0. That will never happen. Okay, because we have no values of the function or the probability distribution that are 0. Now, when m will be 1 over 16, or when 0 is included and x is less than 1. Now, when you include 1, that is this case, then you're going to have 5 over 16 for 1. The next number will be 2. Then for 2, you have 11 over 16 for 2 less than or equal to x less than 3. You have 15 over 16 for 3 less than x less than 4, and then 1 for x greater or equal to 4. Now, we need one more thing for this problem. We have the cumulative distribution defined. Now we need to verify that f of 2 equals 3/8 using the cumulative distribution. Any idea of how to find? Yes, sir. That's correct. So you have the cumulative probability, right? So you know what will be the value of till 2. If you want only the number or the value for 2, then the only thing that you need to subtract is this number minus the cumulative before 2, which is this one. So what you do, f of 2 will be equal to f, or the cumulative for 2 minus the cumulative of 1, that is 11/16 minus 5/16, and that's 3/8. Questions? Let me show you something really quick. So I think that this will give you a better idea, because once you see the figure, you can understand what we are trying to do. So it's helpful to look at the probability distribution in a graphic form. Do you remember how, well, it's right here, this is called a histogram, or a probability histogram. So basically what you're doing is for each outcome you're drawing a bar for the probability. So for x equals 0, the probability is 1/16. X equals 1, the probability is 4/16, and so on. So for each outcome you have a bar. Now, if you want to find the probability of x equals 2, then you go here to the bar and you say it's 6/60, right? Now, when you draw this figure using the cumulative distribution, this is how the figure is going to look like. Now we have the steps. And the reason for those steps is because you are adding or you are accumulating the probabilities for each outcome. So you start with 1/16 here. And once you get to 1, then you need to add this probability plus the probability for 1. So when you add 1/16 and the probability for 2, which is here, 16, then you will get to this point, and you'll keep that probability until you move to 2, 3, and so on until you get to 1. So the function that we're describing here, this function, is represented by this. So if you want to find the cumulative probability of x3, then you know that you're going to look here into the graph, and that will give you this number. Okay? So that's all I have for today. On Wednesday, we're going to start from here, and we're going to discuss some of the problems from the homework, and then also talk about the exam. If you have questions about your previous homework, you can talk to me right now, and we can fix those problems.